Then we also note that the angle A1 should be equal to the angle B2. Again, I'm just using that property of angles in the same segment. I also note then that the angle D1 is in the same segment as the angle C2. And the last pair is the one which is unmarked at this stage, and that will be angle C1 alongside angle B1. These are also angles in the same segment. Um, and that's about it. Nothing is said about the center, so we can't even think about the center theorems, right? No tangent is mentioned here, so we don't even think of the tan chord. We really have the cyclic quad and its properties. So moving on, we're going to look at the first question, and this is a giveaway question. You know by now that once they say to you, prove that this triangle is similar to this triangle, they have already given you a stepping stone, a hint to say, try and show that angle A in the one particular triangle is equal to angle D in the other triangle, and the angle P is equal to the angle P in the other, and finally that one you'll say third angle of a triangle. But if you cannot show whatever you cannot show, at least the first two, or not the first two necessarily, but at least out of the three sets of angles or pairs, three pairs, two pairs will definitely be a given. For the third, you will just say third angle of a triangle. So maybe just to make life easy for ourselves, let us highlight these two triangles. A triangle APB is this triangle. There's A, there's P, there's B, and it's that triangle. Oh, I forgot another cool set of equal angles here. It's vertically opposite angles because those are diagonals and they are straight lines they are crossing. So here you do have vertically opposite angles. And if you want to be a bit extra as well, you could talk about exterior angle of a triangle and all that. Guys, the more you see, the better the chances of you sorting this thing out real quick. Then we're going to highlight the triangle DPC. Here's D, there's P, there's C. And look at this, we are done. So if you did not see vertically opposite angles, you would have probably said um, third angle of a triangle. I'm talking about a P1 and P2. Okay, so that's what I'm talking about, P1 and P2. So we will start off by then saying, okay, in these two triangles, maybe we don't even have to write that. There's no mark for that, but just for uh, being meticulous, if you want to be meticulous and really thorough, you can do that. So angle A2 is equal to angle D2, and these are angles in the same segment, angles in the same segment. And then another one, which we have also indicated, another pair is angle B1, and this one is equal to angle C1. For the same reason, I will be a bit lazy and write that. But please, you are not authorized to do that. You must write your arguments in full. Then look at the third one. You could say, well, this one is quite obvious. P1 is indeed equal to P2. So you have two options here. You could say third angle of a triangle, or you could be more clear and say, well, I do notice that these are vertically opposite angles. If you are not sure that they are vertically opposite, then please stick to third angle of a triangle. Right. So then we conclude that the triangle APB is indeed similar to the triangle DPC. What have we used here? We have used angles, no sides. So your reason must be angle, angle, angle. So that is part one. And then we said, as a result of part one, so as a result of similarity, because we have proven that the two triangles are similar, the following is implied, or this is the result. Well, let's write it down, or let's do those again. AP over DP must be equal to PB over PC, and this must be equal to AB over DC. That's what we said. So let's write those ratios. Therefore, AP over DP must be equal to PB or BP, if you like, over PC, and this must also be equal to AB over DC. And obviously, our reason is because we've got those two similar triangles. So we then look at the question: what is actually what are the sides of interest from this? So we need a DC. We need so I mean, if I need a DC, then that ratio must surely be there, and then I need a PC and a BP, so that must also be there. So guess what? I just need to extract that part of the equation. So this is, I'll then say, therefore, uh, PB over PC is equal to AB over DC, or CD if you like. We then go for Orlando Pirates, we cross multiply, in other words, and then it turns out that PB multiplied by DC is equal to AB multiplied by PC, and the order of letters should not bother you, because this statement is exactly that statement there. So that will be your conclusion for this problem. You got this right, well done. You didn't get it right, please, this is not the end of the world. It does not in any case mean that you cannot do mathematics. Just want to remind you of this beautiful quotation, that which says, that which at first seems difficult, by constant repetition grows easy. When you do something for the first time and it seems like it's difficult, you do not give up. You actually continue to do it until you get it right. This is where musicians would say, practice makes perfect. So please keep practicing. Do not give up. And you struggle, we've got a line, a WhatsApp line, where you can reach out and we can try and help you do a video or even engage in a session. All right. So let's do the second one and see how it was supposed to go. So here we have O is the center of the larger circle. So we've got two circles here. There's a large one, there's a smaller one, or there's a big, small kind of situation. But then we are told about only one center, and this is the center O. We don't know of any other center. They don't give us the center of the other circle. So for the first time in the problems that we have done so far on similarity, for the first time we can think of center theorems now. Okay, DF is a tangent to the larger circle at D. So again, we are, in addition, given a tangent. So really lots and lots of options in this case, and sometimes information overload can actually be problematic. So you need to be really strategic in how you're gonna go about this. One of the things that I'm gonna do for myself here, because there's a tangent, I'm gonna start with all my tangent concepts. And and I'm gonna note that I actually have a radius perpendicular to a tangent here. Okay, and then I do not have a tan chord situation. Please take note of that, because then if that is the case, I would have had a chord maybe somewhere there. Okay, and then there must be an angle subtended by that chord in green, but that's not the case. Of course, you could argue that there is tan chord here around angle D, since indeed the diameter is a special chord. You could argue, yes, that diameter is a special chord. So we do have an angle between a chord and a tangent, but we already have a theorem for that, which says rad tan. But then take note that there is no angle subtended by that chord. So please, we are not going to think of tan chord here. The only applicable tangent related theorem here is the tan rad So we have a 90-degree angle formed at point D. And then I'm also going to check what other theorems talk about the center. We have another theorem which is a special case of the theorem which says angle at the center is twice angle at the circumference. And that theorem, we spoke about it, we said angle in a semicircle. So that is why I've got a right angle at A, at point A, because remember, O is the center of the larger circle and I have a diameter. So there are actually two diameters going through this larger circle. So it's quite important to note that. So that's that. And then another thing I will also start thinking, I have always said to you, also think of your radii, because your radii often bring to life what we call the isosceles triangles. But in this case, looking at the triangles that are formed, it's not really that helpful, because look, you're gonna mark that as a radii, that, but that doesn't really take you anywhere, because you don't have a triangle there, you don't have a triangle there either, you don't have a triangle there, you don't have a triangle there. So here marking radii will not really be that useful at this stage. um, However, we can note some things like obvious things like vertically opposite angles. We could note those things. I think it's also important to pay attention to the smaller circle. There might be stuff there, and I see stuff already there in looking at the smaller circle. I see things like angles in the same segment. You see that G2 and H2, those are surely in the same segment. Nothing is actually said about parallel lines. So I would like to also point that because there's a common temptation. Uh, Students will often then say, no, we've got parallel lines and all that. So please beware that although things might look like, you see, that's another thing about geometry. Just because it looks like it is, it does not mean it is. It has to be stated. If it is not stated, you have to prove it. If it is not stated and you want to use it, then you have to prove it. So please beware of such little things. So we have identified angles in the same segment there. I don't know if I'm leaving out anything else. Anyways, we will see other things as we go. I do not see, at least for the larger circle, I do not see a situation of an obvious cyclic quad, but I do see 4 points that are on the circumference. Okay, so let us be careful as well on this one. Okay, very, very important. Although these are there, look, just wanna, what I'm talking about now, I'm talking about misconceptions. So just make sure that you do not misunderstand what's going on here. So these 4 points on the larger circle, right? Our natural inclination would be to say, oh, there's a cyclic quad, right? Yeah. But now, because of these crossing lines, I know I'm going to have students saying, oh, there are angles in the same segment. Please be careful. There are no angles in the same segment. Because if there's a diagonal, yes, the only two diagonals for the cyclic quad is diagonal AC and is the diagonal BE. But the diagonal BE is not drawn. So do not be tempted to think of angles in the same segment along the soil. It's probably a good idea to maybe avoid this, but there is a nice proper cyclic quad which forms when you look at the smaller circle, and it is this quad here. And this is the one quad where you can actually think of angles in the same segment, because then as a result, angle E will also be equal to angle C. Okay, um, I think let's look at the questions. If there's anything we've left out, we will catch it in the by and by. So the two triangles to focus on here is triangle ABC, which is a right angle triangle. I hope you note that, and it's all triangle DFE, which is also a right angle triangle. And just like that, look at what I've done. The bits and pieces of information which I've actually used, or the angles that I have identified, are actually enough. If you notice, they are actually enough to help me prove that triangle ABC is similar to triangle DFE. Remember, this is a giveaway question. So surely angle A, maybe let's start here. Let's start here. I must actually make this very clear. There was a thinking process. There is a theorem that you used to conclude that angle A is a right angle. So you got to start there. Okay, I don't know what's going on there. Okay, there we go. So you will start by saying angle A. You could actually make an inclusive statement here because these are just, you are using this one and the same theorem, although it's different cases, but uh, although it's different diameters, but you could still do that. So I'm going to go angle A is equal to angle D. And then my reason for both of these will be, angle in a semicircle. Where is it? Half a circle. That's it. Or what do they say? Diameter subtends a right angle. But I don't want to use that long reason. So you have to indicate this thinking process, guys, because you used a theorem. You were never given that A is 90 degrees. You were never given that D is 90 degrees. So because you figured it out using a theorem, it must be stated. Chances are you'll lose a mark if you don't indicate that. All right. Now, therefore, let's go ahead and argue then. Somehow we have actually done this anyways. We have proven this. So that's our first statement. Then our second statement is angle B. No, angle B and F. You see, angle B and F, we don't have a theorem to justify the equality of B and F. I want you to notice this. You're going to waste time if you're going to try and find a way to prove that B is equal to F. But one thing that is quite clear is that I can show that angle C is equal to angle E, and these are angles in the same segment, looking at the smaller circle. This is the cyclic quad which I was talking about. Now, you will then be sneaky and say, well, angle B must be equal to angle F by using the principal property third angle of a triangle. You see, this is how you must argue. And then you don't have to stress much because the correct order was already given in the problem itself. So you will just conclude that, therefore, triangle ABC is similar to triangle DFE. What is your reason? Angle, angle, angle. Done. Problem number 2, we are just proving similarity again. So let's have a look at it. Here we're looking at the triangle CGO. Let's note that triangle. So you see, as a result of our similarity, guys, having been able to prove that the first two triangles are similar, guess what? We can now conclude that angle B is equal to angle F. In fact, we have already concluded it. Another thing that we could use is the ratio of the sides, but they've not asked us something much. But let's mark on the sketch. Let us mark on the sketch. You never know how useful this might be. Let us mark those angles as equal. CGO is this triangle, CGO. Then another triangle to look at is EHO. EHO. Oh, that's going to be a bit chaotic. Okay, I'm just going to remove these highlighters because there's a lot happening. There's some drama going on here. All right, maybe let me use a line so that at least, yeah, the highlighter is quite destructive in this instance. So that's CGO, and then where's EHO? This is E H O. Okay, one thing that is quite obvious at this stage is that angle E and angle C are equal in both triangles. That's one thing that is quite obvious. And another quite obvious thing is the fact that angle O1 is common to both triangles. Guess what? We are done. So we will then say H1 must be equal to G1. So this was actually another giveaway. So we have already established that angle E is equal to angle C, and we said this is because these are angles in same segment. And then the second statement, and then we are done, is the fact that angle O1 is actually common. So my final statement and my conclusion is that angle G1 in the red triangle must be equal to angle H1 of the yellow triangle. And this is using third angle of a triangle. And then the order has already been given, so I will then conclude that the triangle CGO is indeed similar to the triangle EHO. End of proof, if you like. Right. So that's about it for as far as this the homework was concerned. And well done for attempting the homework, guys. This is the only way for you to gauge and actually know whether you are doing the right thing or not. So I encourage you to actually do the homework. I must tell you something as a teacher as well. It's the fact that I know students often want to do the homework to impress the teacher, but homework is actually never about the teacher. It is all about you exercising, keeping fit, ensuring that you know what's going on, that kind of a thing. Okay, let's get to the business of the day then. For today, remember I said we want to check now. What do you do? How do you go about a situation where, yeah, they are asking you to show that this times this is equal to that, or this over this is equal to that over that? How do you go about that when you were never given two triangles to work with? Okay, so this is now where you may say similarity becomes challenging. And but as I said, there is actually a strategy, a way to work around that. And I want to start off with that strategy before we can actually try this example. I just want to do a generic kind of thing, and then we can get into this difficult example. Well, it's not really difficult, but yeah. Okay, my computer seems to be misbehaving. Not sure why. Okay. Okay. There we go. So here's the story. Let's assume that in some situation you are required to prove. Let's assume you are required to prove that the ratio AB over AC is equal to BC over CD. Now, there are at least two possible ways of figuring out which triangles they are referring to here. The first strategy is to make an analysis of the letters at the top and the letters at the bottom and see, are these actually giving me triangles that are in the sketch? That's the whole idea behind this thing. So let's call this the top bottom approach. So here, there's no preceding question that says prove that this triangle is similar to this, and now as a result show that this ratio is equal to that. There's nothing like that. Out of the blue sky, they just say show that this ratio is equal to that. So top bottom approach means you're going to check the the letters that are involved at the top, okay, of your equation. So surely we've got A, B, C. Obviously B appears twice. So then the question then comes, do I actually have a side AB and do I have a side BC? Okay, in a triangle. From the triangles that are in the sketch, do I have a side AB and do I have a side BC? And then you'll do the same thing with the bottom and say, okay, it seems like in the bottom there could potentially be a triangle ACD. Then again, you ask yourself the same question: is AC a side of a triangle? Okay, is CD also a side of a triangle? That's what you will ask yourself. Okay, if if that is the case, then I promise you, you will then go ahead and then establish that, okay, you probably have to show that this one triangle is similar to the other triangle. That's it. Okay. Once you have established that, okay, that's an triangle, then there's a chance that those two triangles are similar. So that's top bottom. The other approach is the left right approach. So let's say here I've got AB. Let us still work with AB. Maybe let me have a different side here. AD, and then let's have here BC, and then let's have CD. So again, here we are saying left right here. The method number 2 is left right approach. So here, obviously, as the name suggests, you check it on your left hand side. Is it actually possible to have triangle ABD? And if there is triangle ABD, do I have AB and AD as sides of that one particular triangle? The same thing with the right hand side. Is it actually possible to handle BCD? If so, do I have the sides BC and the sides CD in existence? If that is the case, then try and prove that these two triangles are similar. So that's all. That's all. All right. As I said, this is the extreme case of similarity where they really don't tell you which triangles are similar, but you have to figure out. And like I'm saying, there is actually a way to figure it out. And here we are. We have a sketch here. We are told in the sketch that the line AP, line segment AP is actually a tangent to the circle at point P. And then furthermore, we have parallel lines. So it's fun time here in this situation. Okay, before we can even think of the troubles that await us. So in other words, showing that PS over QR is equal to ST over RT. Before we can even go there, let us have fun with the information that is given. Let's do that. I've got a tangent, and right at the point of tangency, there's a chord. So here I can confidently, boldly, without any fear, think of the tan chord theorem. So what does the theorem say? It says the angle between the tangent and the chord is equal to the angle in the alternate segment. So angle Q2 is actually subtended by the chord PS. So by tan chord P1 is equal to P2. But then I do hope you are aware now that there are angles in the same segment here thanks to the cyclic quads, the cyclic quad PQRS. PQRS is a cyclic quad. So I don't only know that P1 is equal to Q2, I also know that R2 is equal to Q2 because these are angles in the same segment. So it's quite cool to note that. But not only that, let's go to town with this thing. Let's go and mark all angles that are in the same segment. Angle Q1 is in the same segment as angle P2. We're just making life a bit easier and affordable for ourselves here. Angle S2 is also equal to angle R1. And obviously then the last pair will feature angle S3 here alongside uh, angle P3 and angle P4. Maybe I should mark those with an arc. Right. So I have really at this stage taken advantage of angles in the same segment because the side quad. Um, I should say also you could actually have an exterior angle of S2 quad because the side SR is actually extended. So S1 here should actually be equal to the Q1 and Q2 combined. Um, Obviously, at point T, we have very nice things going on there. Vertically opposite angles are formed. At point M, we also have vertically opposite angles formed there. But you see, we have not even talked about the fan. You know, the fan that is corresponding angles. Where is the fan? I want to write the fan here. You see, we have corresponding angles, we have co-interior angles, we have alternating angles. So there's just a lot of information here. If I start with corresponding angles, remember, uh, you must note that the the parallel lines are to guide you. The parallel lines are to guide you to the relevant lines. Okay, so no, to the relevant angles, not lines. So my parallel lines is PN and SR. So look, this is actually it. N1, the angle N1 is actually equal to angle R1 and R2. This is by using what? The fan now. Use corresponding angles, okay? Not only that, I also have alternating angles. P3 actually alternates with R2. You see, we are not even done yet. The angle M1 here also alternates with angle S3. We just on the fun here, okay? We also have co-interior angles for sure. When you add angle N2 and angle R, that's 180 degrees. If you add angle, you look at angle P2 and P3 together with angle S2 and S3, those are also co-interior. So uh, it's going to be a lot. So let's leave it there for now. Which I think we just kind of have more than enough information at this stage. I've not even talked about exterior of a triangle, but it's there also. It's there. So there's going on here. I do hope you enjoying that. I hope you're enjoying that. All right, let's get to business. Let's apply the principle. Let's see. Okay, I'm gonna start with the top bottom approach. Uh, in for problem A. So I'm gonna do problem A. Once I'm done with problem A, it will be your turn to try problem B. Okay. So please stay alert. Make sure that you actually follow on whatever I'm doing here, because next up it is you trying out and checking that you actually understand the stuff. All right. So the top bottom says I must try and check if triangle PST actually exists. That's what the top bottom approach is saying here. Does triangle PST exist? And looking at my sketch, it does appear that there is a triangle called triangle PST. If I look at the bottom letters there, I've got QRT. So again, my next question then is, does triangle QRT actually exist? And it does appear, by the look of things, triangle QRT exists. If you were to try left right, I just want to talk to someone maybe who would have tried left right and maybe they argued there's a triangle. If you tried left right approach, I want you to notice that the left hand side is already creating a problem for you because on the left hand side you have four points. You have P, you have S, you have Q, R, and that there's no triangle with 4 points. If you get what I'm saying, if you get the picture. So in this case, the top bottom approach actually tends to be the most ideal because that's what as the two triangles we have clearly identified. So um, let's go ahead then and prove that these two triangles are similar. I have a slow computer today for some very weird reason that I don't understand. Okay, so we have tried top bottom. We have identified triangle PST, and we have also identified triangle QRT. So we're gonna make an attempt. We're gonna try and show that the triangle PST is similar to the triangle QRT. This is your aim, okay? This is your aim.